Slides. Thank you for coming. Jim Stone set me up beautifully with his talk on radiation hydrodynamics yesterday, and I'm going to continue in that vein by talking about marrying radiation hydrodynamics to cosmological hydrodynamics. So here's the title of my talk, which is actually the title of a method paper that was recently accepted to JCP. Subtitle could be How and Why We Put Radiative Transfer into ENSO, and I'd like to acknowledge my collaborators here who are listed, principally Dan Reynolds, who is now an assistant professor in applied mathematics at Southern Methodist University. Well, if you can think all the way back to a week ago Monday, you heard Mike Norman, the pundit. Today you're going to hear Mike Norman, the code developer. Indeed, I have devoted essentially my entire career to doing code development. And I thought this was actually an appropriate venue to reflect a little bit on what I've done over the years. You know, when you get to be in your mid-50s, you start looking back and asking the question, well, what did I really do with my life? And it basically boils down to a simple algorithm. Get interested in some physics, develop a code, apply and write some papers, make the code public, and repeat. And this algorithm has yielded this list of codes, which are various incarnations of ZEUS and ENSO over the years. Jim nicely summarized the early evolution of the ZEUS code. We started working on numerical cosmology in the early 90s, and the first code to be produced was a uniform grid code called Chronos, developed by Greg Baryon as his first sort of thesis project. And that was followed by early developments of the adaptive mesh refinement code, ENSO, in the late 90s. And then we took the ZEUS code and made an MPI parallel implementation around the turn of the century. And then so now we just sort of hopscotch between ZEUS and ENSO releases. The first public release of ENSO was in 2004. This version of ZEUS-MP, ZEUS-MP 2, I think might be of interest to many of you because this is it's a 3D parallel radiation magnetohydrodynamics code with self-gravity that operates in Cartesian, cylindrical, and spherical coordinate geometries. So it's actually quite a useful tool, but I don't know if many people know about it because of the ZEUS confusion that Jim talked about. But anyway, all of these codes with the asterisks are available from our website. We made a fresh release of ENSO just a few months ago, version 1.5, and what is coming up next year is a release of ENSO with hybrid parallelism, MHD, and radiative transfer. And we'll also make a release, Dan Whalen and I will make a release of ZEUS-MP 2 with the multi-frequency radiative transfer, some of which I'll be talking about today. So in this vein, get interested in some physics, write a code. What is the latest turn of this wheel? It is combining radiative transfer and ionization physics with cosmological hydrodynamics. And let me set out the algorithm requirements that we had. Basically, we'd like to be able to do simulations like these, where each of these yellow dots would be a source of radiation. And you can see that there's a lot of them. So we would like an algorithm whose cost is independent of the number of sources, scalable with respect to the number of unknowns, that is, the number of grid cells in the computation. And here you're looking at 8 billion. Ideally, we'd like order n scaling. We'd like scalability with respect to the number of processors, ideally order log n processors. We'd like it extensible to AMR, extensible to multi-frequency, not too slow to use. And we have been successful, at least with regard to these first three objectives. We have not yet extended this to AMR. Let me make that clear. And the way we've done this is through the use of highly optimized parallel multigrid. So here's an outline of my talk. First, I'm going to give the scientific motivation, and then I'm going to spend probably half of this lecture on the basics. I won't even be talking about ENSO at this point. I just want to talk about the basics of photoionization, I-fronts, ionization fronts, and ionized flows, which exhibit some pretty interesting and complicated phenomena. I want you to have that in your mind when you start thinking about ionizing the universe. And then talk about some of the methods that have been developed for 3D radiative transfer in cosmology. Obviously, the transfer has to be done in 3D because the universe has no obvious symmetries. And then I'll get to our algorithm, which provides the title of this talk. I would like to point out that this algorithm could be implemented into any hydrodynamic cosmology code. It's constructed in such a way, but I'll illustrate its use marrying it with the ENSO code. We call this version ENSO-RT for radiative transfer. I'll show some preliminary results, and then I'll conclude. I'd like to point out that there is a collection of background reading on the Twiki listed here. This paper here, Reynolds et al. 09, is the full description of the algorithm. Okay, so let's turn to scientific motivation. I'm interested in the effect of energetic radiation, i.e. UV and X-ray radiation, on cosmological structure formation. And we think about cosmic reionization, which occurs at a redshift of about 7 or 8, which changes the intergalactic medium from neutral to essentially fully ionized. This radiation background then bathes all of the halos in the universe, and you could have the depletion of baryons in low-mass halos. Because of this, that can suppress star formation due to the heating of the gas or ionization. Alternatively, if we think about a galaxy forming, it is, in fact, the source of the radiation that ionizes the intergalactic medium. How much of that radiation actually gets out, that's called the escape fraction. We'd like to calculate that. Likewise, radiation from AGN and quasars. So this really focuses on the dense parts of the universe, but what about the rest of it? The rest of it is basically radiation backgrounds in the intergalactic medium. We're interested in the evolution of those backgrounds and the effect on IGM properties. And in fact, it's believed that quasars reheat the intergalactic medium at a redshift of about 3 when they doubly ionize the helium in the universe. So I have a few slides illustrating these points. Reionization, I'm sure many of you have seen this nice graphic made by George Drogovsky. So time runs down. Here is the early universe. Here is recombination. We have the dark ages. And then we have first stars and low-mass galaxies forming, which ionize H2 regions around them. And this picks up speed, and eventually you have a complete overlap of these H2 regions at about 1 billion years into the history of the universe. Thereafter, the intergalactic medium is fully ionized and essentially transparent to optical and UV radiation, which is why the Hubble telescope can see so far. And so without this reionization, we really wouldn't have observational astronomy, at least optical and UV. So here's some questions about this. Timing, when did it begin and end? How did the ionized fraction of the intergalactic medium evolve with redshift? Is it kind of, you know, like the stock market before the crash, or is it something more sustained, like other economies in the world? Topology, what is the topology of ionization before overlap? What is the shape of the last neutral surface? We talk about the surface of last scattering here, we can think of a last neutral surface here. What is the shape of it? How is it corrugated and on what scales? And then finally, astrophysics. What are the ionizing sources? Here's a slide that illustrates a long-standing problem in galaxy formation. What's shown here is the luminosity function of galaxies, this from the 2-degree field survey, and you can see that these low mass, low luminosity galaxies are quite a bit below the mass function for dark matter halos predicted by LCDM models. And it's generally believed that this is due to depletion of baryons or suppression of star formation by the ultraviolet background and stellar feedback blowing baryons out. So is the solution to this missing galaxy problem, if you will, baryonic and radiation physics? Many people think so. And then finally, here's a slide on the late reheating and reionization of the universe. So this slide here shows the number density, co-moving number density of quasars versus age of the universe. And there's this rapid rise and a peak at around redshift 2.5, and then it falls off. This is believed to be the kicker. Here we have, again, the Big Bang. We have pre-recombination. We've got recombination where hydrogen helium is neutral. Then we have hydrogen and helium being singly ionized by galaxies at about 1 gig a year, which is what I've already talked about. But it's believed that at the peak of the quasar counts, we get a second ionization of helium, which gives you an extra heat input into the intergalactic medium. Okay, so that's the scientific motivation. Now let me turn to, I would say, the major portion of this lecture, which is the tutorial part on ionization and ionized flows. And this is actually a fascinating subject. It goes under the heading of classical astrophysics, which some of you may have learned in school, but there may be some gaps in your knowledge. And so what I want to do here is try to fill in some of those gaps. So I'm going to talk about the basics, then talk about ionization fronts, how we simulate ionized flows, and I'll illustrate this with the ZEUS-MP code, not the ENSO code. Talk about I-front instabilities and have a slide on what's called spectral hardening, which is seems like a detail, but it's a pretty important detail. Okay, so the basics. Microphysically, you all know what ionization is. Here we've got the energy level diagram for hydrogen, and we're primarily concerned with diffuse plasmas in space, in which case most atoms sit in the ground state. And so here's an electron in the ground state of hydrogen. Along comes an energetic photon above the threshold energy, and that electron gets kicked into the continuum. Here's an electron in the continuum with some positive energy. It can recombine to any state, any level. If it recombines to the ground state, it emits an energetic photon. Now, the important things to know about this are the following. First of all, the photoionization cross-section looks like this. It is 0 below threshold, then it jumps up, and then it has a nu to the -3 profile at higher energies. And so it's really not too much of an approximation to think of this as a delta function and ask how many photons are there at the ionization edge. And if you count those, you've got a pretty good handle on the ionization rates in the plasma. Radiative recombination, it's kind of like the inverse of this in the sense that the cross-section for recombination is of the energy of the electron minus 13.6 eV is very much like the photoionization cross-section for a frequency E over h. In other words, most of the recombinations occur from electrons whose energies are just slightly above the threshold. And what that means is that if you have a radiation spectrum that looks like this, if you have a radiation spectrum that includes hard radiation, the hard radiation gives the electrons lots of kinetic energy, but most of the recombinations are occurring near threshold, and you get a net heating out of this. Now, in terms of recombinations, I said you can recombine to any level. We distinguish between recombinations to the ground state, which is called case A, because these recombinations emit an ionizing photon. And if you think about it, if you consume an ionizing photon and then recombine to the ground state, you emit an ionizing photon. Nothing has changed in Großen Ganzen. Whereas if you recombine to any higher level, then when that cascades down to the ground state, you get a photon that is not ionizing. And in terms of ionization balance, you can just ignore that. That is what is called case B. And that'll be important in the... Okay, so that's microphysics. Now, macrophysically, let's review the radiation field. Just remind you that it's described by this distribution function we call the specific intensity, I sub nu, which is a function of position and direction. The energy density of photons is just the integral of that over all solid angles divided by c. And the photon number density, n sub nu, is just the energy density divided by the frequency of the photon, the energy of the photon. Okay, so that's basically all you need to know about that. And now let's consider a little cube of plasma. We think of it as optically thin. It's bathed by this radiation field. We describe that with a set of kinetic equations. So let's consider a pure hydrogen plasma that is optically thin. So, thermodynamically it has some density and internal energy, E. It's got some number densities of neutral hydrogen, electrons, and protons. So we describe what goes on with photoionization kinetics here. So the time rate of change of the neutrals is a positive term due to recombinations, which is proportional to NE and P. And here you see I've written the sum over all levels. This is recombinations to all levels. I've split off the recombination to n equals 1 and all other levels. And you'll see why that's important in a minute. So this is increasing the number of neutrals, and then here is the photoionization term, where I is the photoionization rate, which just depends on this cross-section times the number density of photons at that energy, which is just E over h nu. This alpha here is the recombination rate to level n, which is generally a function of the temperature of the gas. Now I want to introduce what's called the on-the-spot approximation. This is one of the greatest cheats of all time. Everyone uses it, and for good reason. Because of what I said about recombinations to the ground state giving you back the ionizing photon that just ionized you with no net change, the on-the-spot approximation says that that ionizing photon gets absorbed locally and therefore does not contribute to the balance. And so what is done is to say that the real time rate of change of the neutrals is just due to the case B recombinations. The recombinations to levels n greater than 1 minus the photoionization term. And we write that this way. So alpha sub B is the case B recombination coefficient times the electron density times the proton density minus the ionization term. So that's the equation you would solve macroscopically for this piece of plasma. And then finally, that process photoheats the gas. Here we have the gas energy equation, time rate of change of the specific energy is proportional to the density times this per particle heating rate, G sub H1, minus the radiative cooling rate, lambda of T, which you can think of as just some cooling function that has been tabulated for you. This per particle heating rate, if we dig into that, we see it's just the photoionization cross-section times the photon number density times the difference between the photon energy and the threshold energy. You got to get the electron out of the atom, and that costs this much energy. This difference is what is available to photoheat the gas. And now you just integrate that from the threshold to infinity, and Bob's your uncle. That's the photoheating rate. Well, it's actually both. It is actually quite a good approximation. If you figure out what the mean free path for that, when you consider that the recombinations come mostly near the threshold, it's a fairly low energy photon. It's 13.6 plus epsilon. If you figure out what the mean free path of that is inside a typical H2 region, it is small compared to the Stromgren radius. And so it's a pretty good approximation. You don't have to do this. You can source a transport solver with that recombination radiation and do that as well, and people have done that. But it's a pretty good starting point. Okay, well, we all know about Stromgren spheres. It's probably the first calculation we do when we take interstellar medium. So, remind you what that is. Consider a point source of ionizing radiation in a uniform medium. It will inflate an ionized sphere of radius r sub s. And where you get that is you just balance the recombinations inside the sphere. There's the volume times the NPNE times the case B recombination rate. You equal that to the photon, the ionizing photon flux. You solve for the radius. And it goes as the 1/3 power of the ionizing flux and 1 over the 2/3 power of the particle density. And this is typically about 20 parsecs for an O star in the interstellar medium. We can actually ask in this idealized problem, how would that ionization front move out to the Stromgren radius? And that's very easy to calculate. In the frame of the ionization front, we just balance the flux of ionizing photons with the flux of neutral atoms. So here's NH times the velocity of the I front. For non-relativistic I fronts, we don't have to, we don't have to transform anything with gamma factors. And therefore, solving for V sub f, you get this expression here, where J is now the photon flux at the front. Okay, well, what is that? Well, it's just the source of photons minus all the recombinations inside that radius. So here's the volume. Consider the point where the front is at r sub f. That's the volume, and then we just multiply by the two ends and the case B recombination coefficient. That's all of the recombinations happening inside of that radius, and that is basically removing ionizing photons from. And then recognizing that V sub f is just drf dt, you can manipulate this and get this nice solution. The radius of the I front is just the Stromgren radius times 1 minus this exponential, where this exponential is t over the recombination time. And the recombination time is just, the inverse of that is just NH times the recombination rate. So here it is. This is plots r over the Stromgren radius versus time and recombination times, and it asymptotically approaches 1, the Stromgren radius, in a couple of recombination times. and here's the velocity of the I front. And one of the reasons why I show this is a wonderful verification test for codes, because you have an analytic solution. I have to point out that this assumes that alpha sub b is a constant. That is, that the ionized gas is isothermal, which is a pretty good approximation. It's typically about 10 to the 4 Kelvin. So there's that. This has been generalized to cosmological I fronts by Shapiro and Giroux. It's a pretty trivial calculation. In an expanding universe, the number density just keeps dropping as 1 over the scale factor cubed. You do the same balance equation for r sub s, the Stromgren radius, and solve for r sub s, and then you stick this law in for the density, and you find that the Stromgren radius is just the Stromgren radius at your fiducial time, t equals 0, times the scale factor divided by the scale factor at the fiducial time. So in other words, the Stromgren radius just expands linearly with the universe. The universe expands by a factor of 5. The Stromgren radius expands by a factor of 5. Now, for luminous quasars, this Stromgren radius is many megaparsecs. Now, you can actually solve the time-dependent problem analytically, which Shapiro and Giroux did. And I won't write down the formulae. They're all in our method paper, because this also is a wonderful verification test. But what's shown here are some solutions. So this is the radius of the I front divided by the Stromgren radius versus log of the redshift divided by the redshift when the source switched on. And this would mean 0 to 1 means the I front has gone to the Stromgren radius. But in general, solutions never achieve that. They increase and then they fall off. And even for this case, where the source switched on at a redshift of 1,000, that's one of those little I fronts I showed in the cartoon. It sits there at its Stromgren radius, but then it falls off. And why is that? Well, it's because the universe keeps expanding. As the universe expands, the recombination rate drops. As the recombination rate drops, the Stromgren radius increases, and the I front finds itself having a hard time keeping up with its revised Stromgren radius. Oh, I got to be bigger now. And it just can't get out there. And so this is an important thing to keep in mind when you do cosmological reionization. Okay, so all of this was without hydrodynamic response of the background medium. Let's turn on dynamics. Well, here we have this nice Stromgren sphere, and let's suppose it was expanding into a medium of density n naught and typical ISM temperature of 100 Kelvin. Say this is the neutral hydrogen near molecular clouds. And now it's photoionized the gas up to 10 to the 4 Kelvin. It's taken each one of these neutral hydrogens and turned them into 2 particles. So now the pressure inside to outside ratio is 200. 100 from the temperature and 2 from the particles. And this drives an expansion of the H2 region. And as the H2 region expands, the mean density drops. It reduces the internal recombination rates, and therefore the Stromgren radius wants to be bigger. And so RS increases. And as this expansion picks up speed, it drives a shock into the neutral medium. And now, suddenly, you've got a situation where an I front has, because of dynamics, split into an I front and a shock. You can think of that as some kind of critical transition in the nature of the front. So let's look into the theory of I fronts a little more closely and consider the jump conditions across an I front. So here we have the I front. We're in the frame of the I front. We have neutral upstream gas flowing in at velocity v1, and it has these thermodynamic properties. And then at this I front, which is just a few photon mean-free paths, which is tiny on the scale of an H2 region, you get ionization, and what comes out is a fully ionized flow, and it has some post-front flow relative to the front of V2 and thermodynamic properties ρ2, T2, and P2. Well, we can just write the pressure as in units of the in terms of the adiabatic sound speed, which is what's done here. Well, this was all worked out by Kahn the year after I was born. So, and this leads to a bewildering variety of I fronts, a lot of solutions, most of which are never achieved in nature. And the analysis is pretty simple. So if we start with conservation of mass across the I front, and remember that this is also equal to the photon flux, the ionizing photon flux. So that's the driver for all of this. Here's conservation of momentum, which, substituting for P, we can write this way. And then solving this for V2, we get this equation, this quadratic equation, which has real solutions only if this term obeys certain conditions, and that's written here. And so now we can turn this into a quadratic equation for V1, that is the velocity of the incoming neutral gas relative to the sound speed in the incoming gas and the post-front sound speed. And this has two real roots, and they're written here. This is the velocity of so-called D-type front, D for dense. This is what a I front moving into dense gas does. And then V sub R, this is the R-type front, so-called rarefied. And if we look at this, V sub D is approximately this, which doesn't jump out at you what that means, but it will in a second. V sub R, the R-type I fronts move at twice the speed of sound in the ionized gas. So converting this into words, these are the properties of the I fronts that we care about. The other 8 solutions that Kahn found we forget about. Turns out that for R and D type fronts there are 2 kinds of each. There's a weak and a strong, but the strong never occur in nature. So we just are down to these 2, weak R type and weak D type. Weak or strong refers to the density jump across the I front. So for weak R type, they propagate supersonically with respect to both the upstream and downstream gas. And that's important because that means there's essentially no hydrodynamic coupling. The weak D type, they propagate supersonically with respect to the upstream gas, but subsonically with respect to the downstream gas, which means that pressure disturbances inside the H2 region can reach the front, and those pressure differences can drive a shock wave into the upstream gas, which means that these kinds of I fronts are strongly coupled to the flow. So to summarize, R-type are not hydrodynamic, D-type are hydrodynamic. In pictures, this is what you have. So here's the neutral gas, and in a weak R-type front, you just get this ionization, and this I front zips along supersonically with respect to both media. In a weak D-type front, you have the way I think about it is this ionized gas is pressurized, this I front is moving subsonically with respect to this gas, so that pressure difference can be felt, and that causes hydrodynamic motions which drive a shock ahead of it. So here you have cold neutral gas, here you have shocked, warmed neutral gas, and then this shock has basically created the right upstream conditions for this I front to sit there and connect the states. So to complete the story of what happens in dynamic H2 regions, you get a pressure-driven expansion phase, and so now it's kind of like a stellar wind, and you can derive a asymptotic solution for R versus T, which is written here. The radius of the I front expands as time to the 4/7. And if we were to follow the evolution of this H2 region over its entire history, it would start when the I front was really close to the star and the radiation was incredibly intense. We have a weak R-type front moving out supersonically, and it transitions to a weak D as it runs out of gas. As the recombinations start to take their toll and the I front slows, you get this transition to a weak D type. And if you look at it very close up, as Axford and someone else did in the 60s, you can see that actually the front moves from a weak R to an R critical, where it's moving just sonically with respect to the downstream gas. And then it transitions to a critical D, and then finally a weak D. And then this expansion will continue until you achieve pressure equilibrium with the ISM. Okay, all of this was in a neutral medium. This isn't very relevant to cosmology. A couple more slides on theory. Franco considered what would happen if you had a density profile like this with a core and then a power law fall off in density. And he found that there was a critical slope, omega sub crit, given by this formula, and in the limit where the core radius is small compared to the Stromgren radius, you can forget this term, so it's basically 3/2. R to the minus 3/2 is a critical case. If the slope is less than that, you still get a finite Stromgren radius established. It'll just sit out here somewhere. And here's a formula for the modified Stromgren radius. However, if omega is greater than omega crit, the I front remains R-type, and it just flash ionizes the cloud. So you can just think of this R-type front, burning out from the source, and then it gets to this steep fall off, and it just keeps going. And so you just flash ionize the whole cloud. And you could think of this cloud as gas sitting in a dark matter halo at high redshift, and you can just, completely ionize it. Now, if the core radius is of order of the Stromgren radius, typically what you get is an R to D to R transition. So you can have quite a bit of physics going on there. Last slide on expectations, expansion of the core shock. If you think about it, you flash ionize this halo, you've brought it all up to 10 to the 4 Kelvin, you've got this density gradient. That density gradient times 10 to the 4 Kelvin times K is a pressure gradient, and that pressure gradient leads to an expansion wave. The whole cloud expands at about 14 kilometers a second, and that expansion steepens into a shock wave called the core shock, and you can derive actually the equation of motion for that core shock given by these formula here. So all of this likewise makes really excellent verification tests for a code. Okay, so simulating ionized flows. Here actually is a nice image of the Tarantula Nebula. The blue is ionizing sources. The green is ionized hydrogen, and the red is X-ray emitting gas, 10 to the 7 Kelvin gas. And this kind of tells you that there's some hydrodynamics going on here because you need shock waves to heat the gas to 10 to the 7 Kelvin. And so this is kind of suggesting, this is kind of what I think maybe an early high redshift galaxy might look like. You clearly need some hydrodynamics to model that. Okay, so how do we simulate this? It's your usual 3 equations of ideal gas dynamics with heating and cooling. And then what you need to do is you need to calculate the ionization kinetics of whatever species you care about, principally hydrogen, helium. So you have this equation here for species advection and reaction. And then you've got gravity, and here are the ionization rates and photoheating rates and closure relations and so forth. You can solve this in many ways. The way we've done it with the ZEUS code is as in all ZEUS codes, split it into a transport step where now we have these conservation laws which are solved in integral form. And this is the new one. This is just species advection, which is done conservatively. And then the source step, you have this stuff. You've got the change in momentum, the change in energy, where you've got the PDV work and you've got the gas heating and cooling. And then you've got to solve the reaction kinetics part shown here. So this now is a coupled set of ordinary differential equations, which is stiff, and it's driven by these recombination rates, which are temperature dependent, which depend on this equation. And then you've got these photoionization terms, which depend on the intensity of the radiation field, which requires a solution of the transfer equation. The only thing that's new here is this bit here, and you can solve this, using your favorite ODE solver. But what we've done is we've developed a backward Euler semi-implicit scheme for doing this quite efficiently. All right, but now let's get to the radiative transfer part, which is what makes this challenging, and introduce this notion of photon-conserving radiative transfer and ionization. I'm sure this has been reinvented a dozen times, but in astrophysics at least, I think we were the first to, or at least in numerical cosmology, we're the first to introduce this. And this is what we've also used in this ZEUS-MP code. The idea is very simple. The idea is to convert each photon removed from the beam into an ionized atom. So it's just a bookkeeping thing. And the benefit of this is the eye fronts propagate at the correct speed, independent of numerical resolution. So here's how it works. So consider this beam of radiation coming along through your grid cells, and in this cell it is being attenuated. This is an ionizing radiation, and it's being attenuated by this cell because of the ionizations that are occurring there. Okay, so the optical depth of that cell, I, is just the number density of neutrals times the ionization cross-section times the cell width, delta x. And then the change in intensity across that cell, delta intensity, is just 1 minus e to the minus tau. And so this is the number of ionizing photons that have been removed from the beam. And all you do is you take that number and create that many ionizations. And then you have a photon-conserving scheme. So how's that done? So here's the ionization accounting in cell I. The number of ionizing photons absorbed is just that change in intensity divided by the photon energy. That gives you a photon number flux. You integrate that over frequency, you multiply by the area of the cell. That's the total number of absorbed ionizing photons. And the photon conservation just says the number of ionizations equals the number of absorbed photons. But now we got to contend with the fact that we're solving some rate equation somewhere else in the code with an equation like this. Time rate of change of the neutrals is some coefficient, the photoionization rate times NH. Basically what you want to do is you want to take this number and convert it into a photoionization rate that you just sort of insist the chemistry solver use. And that's all worked out here, and I'm not going to take the time to go through this. You can study this at your leisure. But this gives you a photon-conserving scheme. Okay, so we've stuck all this into the ZEUS-MP code, which has, as I said, these different coordinate geometries. And we've really made it a very simple approximation, which is that our rays can only move down parallel to grid lines. So we have these situations here. So we only cast rays parallel to the radial coordinate for point sources in spherical geometry, or we can cast rays parallel to the x or z axis if we want to do plane wave illumination of some object. Okay, and here's some of the verification tests. This is a point source in a uniform medium with no recombinations, and that means it will never approach its Stromgren radius. If there's no recombinations, there's no loss of the ionizing flux. And so there is the analytic solution, and after a startup error at small radius, which means small number of cells and small times, after the startup error, the code recovers the analytic solution exactly. Over here, this is turning on recombinations, so now you do asymptotically approach the Stromgren radius for reasons that I still don't understand, but maybe I will. The code predicts the I front radius at early times, but then catches up and finds the right Stromgren radius. I think this is temporal discretization having to do with the rate solver and the ionizations. Fortunately, we have a way of addressing this because the method I'm going to describe next is something that has the ability to reduce the nonlinear residual to epsilon. So we have a direct handle on all of the truncation errors. Let's look at some dynamical flows. Here is an I front moving into an r to the minus 1 density gradient. So here's the density gradient here. And what you have here is this is the ionized gas. There is the I front, and there is the shock front. So this is pushing out into the neutral gas. Here's the temperature. So the shock gets you up to 1,000 Kelvin, and then the I front gets you up to 10 to the 4. Over here, I've plotted a variety of time scales, which are quite different, as you can see, and I'll come back to that, the meaning of that in a minute. Here's an r to the minus 2 density gradient, and you recall that this halo should get flash ionized because it's steeper than the critical omega equals 3/2. it'll get flash ionized so fast you won't see it. Keep your eye right here. This is the temperature distribution in the gas. And in the first frame or two, this will pop up to 10 to the 4. Okay, so that's what I mean by flash ionization. And thereafter, you just have, again, the hydrodynamic expansion. Here is the core shock that I mentioned. Here's the density. The density is going down as the halo is just whooshing out to equalize its pressure with the environment. Point out one more thing. There's the cooling time in green. There's the photoionization time in blue. There's the recombination time in red. And you can see, because of this relatively slow evolution, the photoionization and the recombination time are perfectly balanced. And the cooling time is slightly longer. So this is an example of non-equilibrium ionization and cooling. Well, how do we do all this? We do this explicitly using adaptive subcycling. And I'm not going to actually go through this in great detail since I've got a lot more slides to show. But basically, for any cell, you've got 3 time scales. You've got the chemical time, which is the electron density divided by the change in the electron density. You've got the heating and cooling time scale, which is just the energy divided by the rate of change of energy due to radiative heating and cooling. And you've got the CFL condition for that cell. And so the algorithm is basically to look for the minimum of those time steps and subcycle on the shortest thing, even if that is hydrodynamics. What we have found is that people doing numerical cosmology would subcycle on the chemistry and the radiative transfer relative to the hydrodynamics. But in some cases, in these flows, there is substantial hydrodynamic heating that is happening on shorter time scales than that. So you have to invert the order. And so this algorithm does that. Okay, I-front instabilities. Does that look like a Stromgren sphere? I don't think so. What goes on there? There are a variety of dynamical instabilities in ionization fronts. One of them is called the shadow instability, which is related to R-type fronts. What you have here is there's a little spherical cloud with an underdensity of 50%. That's all. Just a slightly less dense region. Could also be an overdense region, doesn't really matter. And in this case, the I front, what's shown here is the gas temperature. So there's the R-type I front. There's the hot post-I front gas. The I front just races ahead a little bit because the gas is underdense. This simulation is set up to make the R to D transition right here. What happens in this shadow instability is the wrinkles that are induced in the I front in the R-type phase grow into catastrophic dynamical instabilities. So there is the shock wave from the D-type phase, and there's the ionization front. And what's happened is that little ripple has grown due to what are called thin shell instabilities and created these eruptions. There is another kind which is probably more relevant for understanding the observations, which occurs in D-type I fronts, and it's related to the thin shell instability. So the point is, for D-type fronts, you always have a hydrodynamic problem. You've got a shock wave being driven into the neutral medium, And when that shock wave compresses the gas, you get a thin shell, which are hydrodynamically unstable. And then when you couple that with the photons, you get some pretty spectacular phenomenon. So basically, because of the thin shell instability, you change the optical depth of each section of the shell, and where you get lower optical depth, the photons race ahead, and it grows in a self. Here's an even more dramatic case in a steeper density gradient. And this is really what accounts for some of these, pillars of creation sorts of structures that you see in the HST images. Okay, last topic on this tutorial on ionization, the topic of spectral hardening. Everything that I've shown you up to now has just taken radiation at the ionization edge and driven the rate chemistry that way. What if you have a real high-energy spectrum? So here is the structure of the I front for the monoenergetic case. You get a very thin I front. Whereas if you take a hard spectrum, like from a population 3 star has a 10 to the 5 degree black body spectrum, and you consider the photoionization cross-section, then the cross-section drops off as you go to higher and higher photon energies. And that means the higher energy photons can penetrate ahead, and they're not absorbed at this position. It broadens the I front, and it also pre-ionizes the gas. So this is a plot of both the electron fraction, the ionization fraction, and the temperature in a typical I front. And so you can get, you will actually have full ionization back here, but you'll have partial ionization running ahead of the front. And those electrons can catalyze all kinds of cooling and chemistry. And cooling and chemistry can make the shell thinner. And when you make the shell thinner, you have the thin shell instability. And in fact, that's what was going on in the previous movies. So it is all fairly complicated. And then finally, if you have a really strong, really hard source like a quasar with a power law spectrum, you broaden the front even further, but the photons are so energetic that the photoelectrons they create have so much energy that they can ionize other atoms. So this is what's called secondary ionization. And you get so much secondary ionization, here's the electron fraction, that it fills this in. So you sort of get back to this case, except the I front is moving ahead faster because of this secondary ionization. Okay, so keep all of that in mind when you think about reionization of the universe. This is what is really going on small scales. Okay, cosmological radiative transfer, a few slides on that. So here's the transfer equation. This has been shown a couple of times already by Volker and by, well, I know Volker showed it. So it's the usual, this is the time-dependent equation for this specific intensity. And here's the new term due to cosmology. You've got the cosmological redshift, and then you've got cosmological expansion, and this is driven by the expansion factor here. This h of t is the Hubble parameter, which is not a parameter, it's a function of redshift, and it's given by the solution of the Friedmann equation. So h is a dot over a. And on the right-hand side is emissivity minus absorption. These spatial gradients are taken with respect to a coordinate which is co-moving with the expanding universe. So that's the cosmological radiative transfer equation. However, one can quite generally make a local approximation and get back to the familiar equation. So how does this work? Well, prior to complete reionization, the size of individual ionization regions are small compared to the cosmic horizon. And in that case, the gradients in the radiation field are of order 1 over the mean free path, photon mean free path. This ratio, which is 1 over the Hubble horizon, is therefore much, much less than this. So sorry to use the 1 overs. LH is much, much greater than lambda mean free path. And then this A bar, which is the ratio of the redshift when the photon was emitted to when the photon was absorbed, that ratio is essentially 1 because the photon doesn't get very far. The universe doesn't expand very much between emission and absorption. And when you take these into account, you throw away the cosmological term and you get back to the ordinary transport equation, which is what virtually everybody solves. I will just say that we want to solve this equation because we want to be able to go from the pre-ionized universe, where the bubbles are small, to the post-ionized universe, where the medium is transparent and you're building up a radiation background. So that's one difference between what we do and what everyone else does. So this slide summarizes some of the methods that have been developed for doing 3D radiative transfer in cosmology. They're all solving the static transport equation. Sorry, not the static. They're solving the transport equation without the cosmological terms, other than doing the gradients and co-moving coordinates. The most popular is this adaptive ray tracing developed by Abel and Vondel. And that's shown here. You have a point source here, and rather than shooting out long rays where you'd really oversample the cells close to the source, they do something intelligent, which is to have a small number of rays, basically 1 per grid cell, and then when they get to larger radius, they split the rays into a quad tree. So they've got a quad tree data structure for the rays. There's also Monte Carlo, which I won't talk about, and then there are the moment methods, first introduced by Gnedin and Abel, and we've done some work on that ourselves. So this adaptive ray tracing is very powerful. It's been used, for example, to do this self-consistent simulation of the growth of an H2 region around a population 3 star. This is high redshift, small scale. This is 3 kiloparsecs. Here you see the halo that forms the POP3 star. And using adaptive ray tracing and an explicit chemistry solver, they've been able to calculate the growth of this H2 region around this star. The adaptive ray tracing has also been used to post-process density fields. Typically what's done is to run an n-body simulation at very high resolution or high number of bodies on very large scales and create a density field. So then the particle densities are gridded, and that gridded density field is then searched for peaks, and radiation sources are introduced at the peaks. And what people do is they propagate these R-type fronts throughout the universe, and you get this kind of reionization picture here. Ilyev et al. Have done this, and other people have done this. The thing I would like to point out, however, is that this is really a cheat. The I fronts are assumed to be weak R-type everywhere and at all times, which is certainly not the case. If you think about it, by the time the I fronts have gotten out into sort of the mean intergalactic medium, on average, this density is constant, and therefore, just on simple grounds, it should start to slow down. Of course, the universe is expanding, so exactly whether it slows down or speeds up is what needs to be calculated. The other thing I would point out is that the cost of doing this is proportional to the number of sources, because you have to have one of these little adaptive ray, you have to have these adaptive rays going out from every single source. And so this is obviously scales with the number of sources. One of the things that makes this a little sketchy is what is called eye-front trapping. What I'm going to show you here is there is a dense cloud sitting right here, which you do not see in this temperature plot. And then there's a plane wave of ionization off to the left. You'll see an eye front moving rapidly to the right, and then it will encounter this dense cloud, and the eye front will be trapped, as it's called. So this is the ionized gas. There's the eye front. There's the eye front, and there's the shock front. What's happening is the eye front made an R to D transition as it encountered this dense cloud, and it is now driving a pressure wave, i.e. a shock, into this cloud, and the cloud itself is casting a shadow. And if you think about what's going on globally in the universe is the universe is lumpy. It's filled with dense clouds, i.e. halos. And as the radiation is moving out, it's encountering this sort of thing on all scales. And so the way that that is taken into account in these post-processing simulations is to calculate what's called a clumping factor and modify the recombination rate. So the recombination rate is increased by the clumping, but it's just coarse-grained, and that's what is done. The other method for cosmological radiative transfer is moment methods, and this I know has been introduced twice, once by Folker and once by Jim Stone. And basically, you combine the 0th and 1st moments of the radiation field and their governing equations, and you get this anisotropic diffusion-looking thing for E sub nu, the energy density of the radiation, where the anisotropy is encoded in this Eddington tensor. And we've done some work on this. This is what you do when you do VTEF, and in this calculation we actually calculated the Eddington tensor self-consistently from a solution of the formal equation. And you can see that it casts shadows. They're not perfect shadows, but they are shadows. Whereas flux-limited diffusion, the radiation comes in and just sweeps over this like water, and you get radiation filling the shadow. We've applied VTEF to the problem of helium-2 reionization, and that's shown here. We assume a quasar population that evolves with redshift, and we calculate the expansion of the helium-3 spheres. We have 3 frequency groups, and we use this analytic Eddington tensor from the OTVET scheme. We calculate the gas photoheating. But in this calculation, this is not done dynamically self-consistently. We also have post-processed the density field from a hydrodynamics simulation. And so our goal now is to make this self-consistent. Okay, so how do we do this? This gets to this new algorithm developed by Dan Reynolds and others. So the goal is to create a parallel scalable solver that couples everything together self-consistently. And the way we've done this is by creating essentially 2 codes that we iterate between. There's the code that does explicit cosmological hydrodynamics, in this case the ENSO code, and then there is this code that does an implicit solution of the radiation transport, the chemical ionization, and gas photoheating. And so it's not just radiation transport, it's radiation transport plus what it does to the gas, and the reason for that is because of the tight coupling. Okay, so I'm going to now walk through this algorithm rather quickly so I can show you some movies. So again, this is the radiative transfer equation with all terms. We take this and we calculate angular moments. And we use flux-limited diffusion, which I just told you doesn't cast shadows. So why am I using flux-limited diffusion? The next slide addresses that. Anyway, once you introduce this ansatz, that the radiative flux is some constant or some function d times the gradient of the energy density, this d is this complicated thing that is a function of gas energy, radiation energy, and the gradient of the radiation energy. It's designed in such a way to give you the correct behavior in the limiting regimes. Once you've done that, you get this equation here. We throw that term out because it's not necessary, and that gives you this equation. So here it's this advection of radiation energy, diffusion of radiation energy. Here's the cosmological terms, and then there's sources and sinks. Okay, so that's our master equation. Notice this is subscripted with the frequency. This is the monochromatic equation, which in the fullness of time we will solve multi-frequency. But for now, we just want to get started with this. So we have a one-group approximation where we assume some spectral shape and basically do a separation of variables such that the energy density, space, time, and frequency is some gray radiation energy density at position x and t times some spectral shape, where this can be a delta function, a black body, or a power law. Okay, so once you put that ansatz in there, you get this equation where this m depends on the spectral model. Why use flux-limited diffusion? Well, here's some reasons. First of all, it was invented by my thesis advisor. Not many people know who invented flux-limited diffusion, but it was Jim Wilson. It's simple and easy, no formal solution required. It gives correct behavior in limiting regimes, gives you causal propagation of radiation energy. And here's the key point. I am interested in large volumes and many sources where, on average, the radiation is diffuse. It's coming from many sources. And so a diffusion approach kind of makes sense. I'm not so interested in the shadowing effects, although let me just say that the essential complexity of this algorithm has nothing to do with the bandedness of the matrix. It has to do with coupling with chemistry and ionization. And so we can extend this easily to the VTEF framework, and it doesn't bust the paradigm of this algorithm. The flux-limited diffusion gives you a symmetric positive definite matrix for which there are very efficient solutions. Okay, so good, I'm on time. So here's the grand system of equations. Conservation of mass, momentum, energy, species, reaction advection, radiation diffusion, gravity, closure relations. How do we proceed? Well, we do operator splitting, but not in the usual sense. We just split those system of equations into two halves. So we take the gas energy and we just split it into EH plus EC. EH is the gas energy due to hydrodynamics motions, and E sub c is the energy correction due to coupling with radiation and ionization. So you stuff that into the gas energy equation, and then you split it into two parts. And you take one part and you put it with the hydrodynamics, and you look at this and you go, oh, well, this is what we do all the time. We solve a gas energy equation. Here, this is the cosmological expansion part. And the rest is all standard stuff. We do the conservation of species, a part of this here, and we advect the radiation energy. So all of this is what ENSO already does. So that's given to ENSO to do. And then the rest is an implicit coupled system. So we have a non-equilibrium multi-species model where we have a correction to the gas energy due to cosmological expansion and photoheating and radiative cooling. We have the stiff chemistry, and we've got the diffusion of radiation. I should say that we also have the option of doing without the rate equations, and we have an LTE model, otherwise known as a two-temperature model, where you just solve for the gas energy and the radiation energy as a coupled implicit system. So we can do, radiative shocks and Marshak waves and what have you, just regular radiation hydrodynamics. The temporal discretization is this theta scheme, generalized Crank-Nicholson, where you introduce this theta parameter, and the implicit part is weighted with theta, and the explicit part is weighted with theta minus 1, and we can vary theta from 1/2 to 1. And so here it is. We're implicit in gas energy, species, and radiation energy density. Okay, I'm going to kind of race through the solution algorithm because there's just a lot of stuff that you can study at your leisure. It's standard stuff. There's only one sort of cute thing that I got from my applied math guy. So the nonlinear solver, it's a global inexact Newton, where you have this function of your solution vector, which is a nonlinear function. So here is the implicit operator, and here all the explicit stuff is in the G's, and we're just looking for a set of u's such that f of u equals 0. And so you do this outer Newton iteration, and that results in a linear system of equations that have to be solved on the inside. Here's the cute part. It's called the Schur complement. For our system, gas energy, species densities, and E, the Jacobian of the matrix has this structure. So here are the partials of gas energy with respect to itself, with respect to species concentration. So it looks like this, and the only elements of this that have spatial coupling is the diffusion equation. That's JEE. So that can be written into this form, where D is this diffusion submatrix. Well, without going into too much detail, you can manipulate this in such a way that you effectively, because you can invert this matrix analytically, you can essentially solve for these variables, E and N, analytically and stuff them onto the right-hand side of this matrix equation. So here is the matrix equation for the gas energy, E, which is the diffusion solve. And the matrix gets modified by the solution of these analytic problems, and they also show up on the right-hand side. So that's called the Schur complement. And that allows us to convert this whole thing into a single scalar solve. And for that, we use multi-grid preconditioned conjugate gradient. And there's too many words here to go through. Let me just say that we use the hypersolver library developed by Livermore, which is a collection of many, many multigrid and Krylov methods that have been made scalable for the largest computers in the world. They scale to over 100,000 cores. And so this is a case where actually you do want to use a library, especially if it's, you know, something that allows you to scale. And so we've built our solver on top of Hyper. Let me show just a few verification tests. Here's free streaming radiation. The step function is the analytic solution, and then as a function of the number of grid cells, you get various amounts of smoothing of this. It is true that FLD gives you a very broadened eye front, but it propagates at the correct speed. Okay, now here is the first delight. I was actually really amazed by this. This shows the static H2 region expansion problem. R over the Stromgren radius versus T in units of the recombination time. And the different line types are different mesh resolutions, and the boxes are the analytic solution. And we get the solution to incredible accuracy independent of resolution. Just bang on. And I think that's because, you know, we have total control over convergence of the nonlinear residual. And Dan has designed this scheme in such a way that it will iterate until it beats that down to 10 to the minus 10. So we've got complete self-consistency between the radiation, the ionization, and the heating. And that gives us this result. This shows the, this is actually the error in the eye front position, normalized by, so it's the difference between the analytic and the numerical divided by the analytic, and this is 10 to the minus 3. And some of the coarse resolution results are hard to see here, but they're sort of up here, and we get second order convergence to less than 0.1%, actually 0.05%. 0.05% at 128 cubed. We turn on hydrodynamics, and we do this expansion into the uniform medium. You don't approach the Stromgren radius. The pressure inside just keeps pushing it out, pushing it out. This has no analytic solution, although it does have an asymptotic, you know, it has an analytic solution in the R-type phase, and it has that offset power law solution in the late time phase. All the variables are involved here, and you see that, again, we get incredibly fast convergence to the solution. There's what it looks like on the mesh. There's the density field, here's the temperature field, and you can see very nice, sharp interfaces in spherical shape. Here's the cosmological H2 region. It's funny, and Dan chose to make this, the simulated, the solid curves, and the dots, the analytic solution. It's reverse what normally you do. But anyway, we reproduce that beautifully. And then here's the best news of all, that this algorithm is scalable. This is a weak scaling test where we put one of these H2 regions in every tile of a weak scaling experiment. So we have a grid of H2 regions expanding. And so this is the wall clock time for the job versus the number of processors. And this is not a log scale. This is a lin scale. And so here we have the usual multi-grid behavior where the sequential portion dominates, there's some sequential portion for the multi-grid setup, which you see here, and then as you increase the problem size, you get this slow turnover. So here you have a problem that's 4,000 times bigger, running in basically 60% more wall clock time than the one processor result. So that's the scalability. Okay, well, I've only got a few minutes left, so I think you're just going to get a gestalt here in 30 seconds. I'm not even going to speak to this. I don't have to. I think many people know about ENSO. There's a 4,000 cube simulation. Okay, so I just want to get to the results. Maiden voyage of this combined solver. This was only made operational last week, so this is a hot off the press. So we just ran a small box, 8 megaparsec. We initialized it at redshift 100. There's 256 cube particles and cells, no adaptive mesh refinement. This gives us a dark matter mass of 1,000,000 solar masses, which means we'll have 1,000 of those in a 10 to the 9 solar mass dwarf galaxy. The proper spatial resolution is 4 kiloparsecs, which is not great, but it's not too bad. And we use this modified Chen-Ostraker star maker where we don't use the Jeans length criterion, the Jeans mass criterion. And then we just grid the emissivity from the stars, which is given by this formula. You just take the star formation rate times c squared multiplied by this rather typical number, and we let her rip. And since I'm short on time, I'll give you the crappy version of the movies. Something was wrong with the way these were encoded, and they play really fast on this computer. I have to fire the graduate student. But anyway, he's been up day and night making these movies for this talk. So first I'm just going to show the point sources. So it starts at a redshift of 82, and you can just watch that counter. Okay, so you get lots of galaxies forming. They look a little scruffy because of the coarse grid resolution, but they're increasing with time. We stop at a redshift of 5. Okay, so here's the radiation energy density. And before I show this, let me just say that it's an 8 megaparsec box. So at redshift 7, it is 1 megaparsec proper. So that's 3 million light years. And the frames are 3 million years. So every frame, we basically have enough time for light to go across the box. And so you're going to see radiation just go everywhere. And by the ending redshift, the radiation is everywhere, which is what an ionized universe looks like. Okay, now this is the ionization fraction. Let me just warn you that some of the frames got out of order, so you're going to see a bit of a stutter step effect here. Again, it's because green graduate student, late at night, first time. It's what it's like when you're in the trenches, man. Anyway, I'm going to replay this and stop it. Okay, so the first thing that happens is structure formation is collisionally ionizing dense regions. So that's what this is. That's important because then the gas can cool and then make stars. And here you see the first H2 region being created. And then there are more and more of them. And then finally, this is the coolest movie. I saved the coolest movie for last. This is the density field. And that's cool enough to play again, isn't it? So the usual structure formation, but now you see all kinds of modulation of the density field by the photoionization. So what's it all mean? I don't know. We just got the movies 2 days ago. Looks like the code is working. You know, I just want to share with you what it's like to develop a code and then finally get it working. When you get the first results, it's all new. It's like, huh? And so that's actually the moment I live for. This is so cool. I love this. It's like first light on a new telescope. We need some time to get to know our new instrument, but it looks pretty exciting. There's hints of substantial modification of the Baryon distribution in filaments and voids, and it's possible that we will have regulated star formation on a cosmic scale. So the next 12 months should be a lot of fun digging into this. So here are my conclusions. Sorry I'm a little late, but we've done a self-consistent radiation hydro simulation. These are now feasible because of some physical simplifications, the FLD, scalable linear solvers, and implicit time integration, which means that we can march this on the hydrodynamic time step. The radiation solver takes about 50% of the runtime, i.e. it doubles the cost of the computation. So, I mean, I agree with Franz Pretorius that you can solve these elliptics in line with the computation and it's not going to kill you. But you have to use these very efficient methods. Next steps are to extend this to AMR, extend to multi-frequency and multi-group. And then one of the things we're working on right now is developing a hybrid code where we do ray tracing on the small scales in the adaptive mesh hierarchy. And then when the rays poke out to the root grid, we hand the photons over to the FLD solver to do the background. And that should be very efficient. So let them shine. Thank you.